you got right and got wrong in Apollo 13?
Thank you very much. So, did we like the movie? It's a pretty great movie, isn't it? And I'm going to preface all of this by saying that it is mostly right, okay? So first of all, it's a true story. So it's not like some of the movies that we've been critiquing. The premise is generally sound. And actually, an awful lot of the dialogue in this is directly ripped out of the transcripts of the actual mission log. So it's pretty accurate. But that is not to say that I can't pick holes in it, of course, because that's what I do. Now, as I said, I'm not going to get too hung up on the accuracy of events. Obviously, there's time compression, the usual things they do in movies. I care about physics. Do the laws of physics hold up in this movie? Spoiler alert, mostly. But we are going to start off just briefly with a little bit of history, since these events took place before probably most of this audience were born, including me. So let's talk a bit about what the Apollo missions actually were. The Apollo missions, this is the missions that took us to the moon, started with Apollo 1, which was mentioned right at the beginning of this movie. We see a dramatization of Apollo 1, which never actually went into space. It was due to launch, doing a pre-flight test when the fire that's referred to in the movie occurred, killing all of the 3 astronauts on board. So when we hear in this movie that an American has never died in space, technically true. They died on the ground, but they were still astronauts. So Apollo 1 never actually went into space, but the widows of the astronauts requested that they get to keep the name Apollo 1, and NASA said, yeah, that seems fair enough, all things considered. So that is still referred to as Apollo 1. Because of that fire, Apollos 2 and 3 got cancelled, and then 4, 5, and 6 went ahead, but they were uncrewed, so they're not interesting. But Apollo 7 really did happen. This was in October 1968. It orbited for 10 days, and it was testing things like whether the spacecraft and crew could last long enough for a lunar mission. Turned out they could, so that's all good. So then we get to Apollo 8. This was referred to in this movie. This launched on December 21st, 1968. It was up there for about 6 days, so over Christmas 1968. And Jim Lovell was the command module pilot on this mission, who's the commander of Apollo 13. So he actually did 2 trips in which he went all the way to the moon, circled around and came back, and never actually got to walk around on it. He does say in this movie, we came so close with Apollo 8. Yep, he came really close again. We then get to Apollo 9, this is March 1969, and when you're hearing these dates, isn't it amazing how quickly all of this happens? And I mean, the fact that the very first Mercury launch was, 1961, and 8 years later they're on the moon? Imagine if we cared that much about investing in science now. This is becoming a common theme in these talks. So where are we up to? We're on Apollo 9. So this is March 1969, again, 10 days. This one was to test the Lunar Module. Apollo 10, this is May 1969. This is essentially like a dress rehearsal for the moon landing. They get all the way to the moon, they start descending, they almost get there, and then they come all the way back. So again, this is kind of like taking your kids to the gates of Disneyland, taking a picture, saying, right, you've seen it, let's go home now. And then, of course, we get to Apollo 11. None of you have heard of this one. It didn't do anything important, really. Just, put a couple guys on the moon, like you do. They followed that up just a few months later, November 1969, with Apollo 12, which also went to the moon and did some more experiments. And this, I guess, is why they refer in this movie to moon landing missions being routine. So, as exciting as a drive to Pittsburgh or whatever the TV channel said. So we then get to Apollo 13, which launched on April 11th, 1970. And by this point, no one cares about moon landings, right? Unless things go horribly wrong. So let's have a look at Apollo 13. This is the real Apollo 13 on the launch pad in April 1970, all tucked up there inside the Saturn V rocket. Now, the thing that's interesting that I wanted to point out is all the way up here, that's an oxygen tank. It's sitting here on the launch pad, obviously pretty far along in its launch sequence at this point. And unbeknownst to anyone, there is a frayed wire sitting in that oxygen tank, just waiting to become a bomb. As Tom Hanks says in the voiceover at the end there, this was a mistake that occurred about 2 years before the mission. No one knew about it, but it was a disaster waiting to happen, even at this point. Now I also wanted to show you the spacecraft. This is the best kind of side-on view we get in the movie, and it is backlit, sorry. But this shows you all the different components of the spacecraft that are referred to throughout the movie. So we have the command module. This is the tiny little cone-shaped bit, which is what they use for re-entry at the end of the movie. This bit here is the surface module. This is where everything went wrong. This is where the explosion took place, where they blew off an entire panel. And up at this end, that's the Lunar Module. That's the bit that's designed for landing on the moon. Now, one thing that's kind of interesting is a lot of people have obviously analysed this incident to death, and most people are fairly convinced that had this explosion happened any earlier or any later, the astronauts would have died. Any earlier, they would have had way too much time to make all their supplies last to get back. Any later, and they would have taken that lunar module, landed on the moon, and they wouldn't be able to use it as a lifeboat. So it's kind of an amazing coincidence that this happened at exactly the right time, that they were able to make all of this work. Now, one thing a lot of people ask is, why did they carry on and go around the moon and come back? And this is addressed in the movie, but like everyone's shouting over each other and it's kind of difficult to figure out what's going on. So I wanted to talk about that briefly. So here's the Earth. Here's the moon up here. They've followed this line, and this little X here is where the explosion happened. So they're almost to the moon, like 200,000 miles away at the point this happens. And at that point, you've got two options. You can do this little maneuver here. You can just about see that little line he drew. That would be a direct abort. What you have to do that, you're already going very, very fast. You're hurtling towards the moon. You have to fire your thrusters backwards to slow you down, and then again to head back in the opposite direction, where you kind of do a little loopy thing back this way. Now, the problem that they do briefly mention in the movie, but again with lots of people shouting over each other, is that in order to do this, they would have to burn the main engine, which is on that service module, the thing that had the big explosion. And at this point, no one really knows what happened. Just something catastrophic happened to that service module. So it was way too risky to fire that engine. It could have made everything explode again. As well as anyone has been able to figure out, that would have turned out to have been disastrous. So it's a good thing they didn't do that. Now the other option, if you can't abort, is to do what they refer to as the free return trajectory, where you loop around the moon up here and slingshot back. So those of you who are at the Martian screening will remember the very cool demo of a slingshot maneuver with a stapler. This is exactly the same thing. So Rich Pennell could have just referred to this movie, except they're slingshotting around the moon, not the Earth. Now, this is much easier to do. You're using the moon's gravity to assist you in sending you back to Earth. But the problem is it takes a lot longer. So they're out there for several more days, and as we saw, that becomes a problem because they're limited on water, on power. Their CO2 scrubbers are running out. So it was very, very risky, but obviously turned out for the best. Now I wanted to have a quick look at the launch in this movie. This is one of these areas where I am not claiming they made mistakes. I'm claiming they used artistic license. So I want you to watch this launch sequence, and then we're going to watch the real launch and spot the difference.
10, 9, 8, 7, 6. Ignition sequence start. 3, 2, 1. Ignition.
Now let's take a look at the real launch. Obviously won't be as high quality as that video.
T-minus 25 seconds and counting, and Apollo 13 is go. T-minus 20 seconds, T-minus 20 seconds and counting. 17, guidance release. 15, 14, 13, 12, 11, 10, 9, 8. Ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13. The Saturn V building up to 7.6 million pounds of thrust, and it has cleared the tower.
All right, so any differences between those launches other than the cinematography? First of all, the countdown is not counting down to the ignition. As we saw in the real launch, the ignition sequences started at T-minus 8.9 seconds, not at 0. The other thing you may have noticed in the movie launch is all of these gantry arms, the big red things that you see swing to the side, are released one by one for some reason. In a real launch, of course, they all release at once. Finally, the thing that actually happens at T of 0 is the hold bolts are released, which allows the whole thing to go up. For some reason, not only does this happen after the clock has started, they even say the clock has started, and then you see the hold bolts release. So, not a perfect launch. But as I said, I don't think this was a mistake. They had way too many consultants and, of course, real footage to have got this wrong. I believe it was artistic license. It's more dramatic if you have all the explosions going off at the end of the countdown and all the gantry arms swinging away as the music is swelling. I assume was a deliberate choice, but still, obviously, something I'm going to pick up on. So let's talk about the moon. Now, this is a movie about a mission to the moon, so we would assume that they understand how the moon works, right? But the fact that I've brought it up is already telling you, oh no, they got the moon wrong. So let's have a quick look at some of the shots we get of the moon. And I'm not cheating here. All of these shots are from while they're on the mission between the Earth and the moon. So this is all within the space of, 6 days. Right, here's one. You see the tiny, thin little crescent. Here's one that's getting more towards a quarter moon. That looks like a full quarter to me. Back to a crescent. These are in chronological order. And then we have a full moon. All in the space of 6 days. Now, you're all nerds. That's why you're here. So you understand that's not really how the moon works. Fortunately, NASA makes really nice visualizations of how the moon works. So let's have a look up at the top left corner here. This is the Earth rotating very, very fast. It's obviously sped up. And the moon is orbiting once every 28 days. Now the sun right now is, I don't know, somewhere around where I am. So you can see both sides are being lit up at the same time. This turns out to be important. It takes 28 days for the phases of the moon to change. Anyone on the planet on a given night sees the same phase of the moon. Anything else we're missing? This big shot in the middle shows you the phase of the moon, in case you can't do the translation in your head, which I can't. If you're standing on the Earth, this is the phase you would actually see. So, first problem, if they're traveling between the Earth and the moon for 6 days, the phase shouldn't really change very much. It's certainly not going to go from that first sliver all the way to full in the space of 6 days. And things actually get even weirder than that.
We expect loss of signal in approximately 10 seconds.
So on Earth. Catch you on the flip side.
So it is true that if you go behind the moon, you're going to lose signal. So far, so good. It is also true that there is a far side of the moon. This is a side that is always facing away from us. The moon is what we refer to as tidally locked. It always shows the same face to the Earth. But that's not, the far side of the moon is not the same as the dark side of the moon. They are very, very different things, although they often get conflated. If we are seeing a new moon, what that means is the sun is currently behind the moon, and so the back side, the far side that we don't see, is currently lit. So the only time the dark side and the far side of the moon are the same thing is during the full moon, when the side that's facing us is fully lit, so the sun, I guess, is behind us, and then the far side of the moon is also going to be dark. At the time when Apollo 13 was orbiting the moon was not full. So therefore, as they're crossing over the terminator, that's the difference between the light side and the dark side, that is not the same as crossing to the far side where they lose signal. I guess it looks cool though, or something. So more weird moon stuff. We have this shot here, very, very nice scene, unless you're getting distracted by looking out of the window, when you will notice a full moon. So that's problem number one. Problem number two though, same scene, we move our over the shoulder shot to face the other way. Now we're looking at Tom Hanks, and right here we have a full Earth. So I forget what they're worrying about at this point, it's probably cold or something. I have a much, much bigger problem going on in my head, which is, hang on, if the moon is full, that means the sun is on this side of it. If the Earth is full, the sun is on this side of it. So the sun is in between the Earth and the moon. This is kind of apocalypse material. Like way, way, way bigger than any problem they're having on this ship right now. Now for something really, really nerdy. Now we see they have to use the Lunar Module as a lifeboat. And in order to do this, because it's the 1960s, they got to do math. So they have to transfer all the guidance system numbers from the command module to the Lunar Module. And we see Tom Hanks filling in this little checklist. What he's doing is calculating gimbal angles. And you have 3 columns here. These are the 3 gimbal angles, and he's converting them from the coordinates using the command module to those on the Lunar Module. Now this is a real checklist. And it just so happens that if you go digging around, you can find the real one. This is the actual one completed by Jim Lovell, which sold at auction for something like $388,000. And you can check his math. And you can see, let's look at this one. This is the outer gimbal here. We do 300 minus, the roll cal angle here is minus 2 degrees. This gives you 298, which you scribbled in just underneath. This is the number from the guidance system in the command module. There's a little minus there, so we're subtracting that. Modulo 360 degrees, so you can see to help him do that up here, he's done 298 plus 360 gives you 658. 658 minus this number here is 302.43, which he's written in here. Now let's go back to see what Tom Hanks wrote down. He's written 355.57 in the Lunar Module spot. That's the command module number. So, first of all, he's putting the wrong numbers in. Second of all, fortunately, he realizes that his faculties are maybe not with him, so he calls down to Houston to check his math. Now, you can check out the transcripts of when the real Jim Lovell did this, and he does exactly what you would expect. He reads out these numbers. These are the Lunar Module numbers, the ones he's trying to calculate. And then he says, hang on, I want you to check my math. So he gives them these numbers and gets them to verify that they get the same answers he did. Now, in the movie, when Tom Hanks does this, all he does is read out these numbers, which, as we see here, are the ones that have been read off the command module guidance system, and asks Houston to check them. Well, he hasn't told them what answers he's got, so it's really unclear what they're checking this against, and all they do is come back and say, yeah, your numbers are good. Well, congratulations, you successfully read them off the guidance system. That said, I'm not really sure what they even thought they were checking, because this is all addition and subtraction, and they're using a slide rule. Now, I'm too young to have ever used one of these, but I know you don't use them for addition and subtraction. So, some weird math going on here. But now we're going to talk about gravity. As those of you who've been to a few of these screenings will know, this is one of my favorite forces, especially when it comes to movies. But this movie gives me an excuse to talk about the equivalence principle, which is a cool thing that comes out of Einstein's theory of general relativity. And it also allows me to use some really cool PowerPoint animations. So let's imagine you're an astronaut in a box. This is a completely sealed box, you can't see out of it. And you're falling in a gravitational field. You're still falling. I need to talk longer than I can make that fall. So the little movement lines mean that it's still falling. Now, imagine instead you are also an astronaut in a sealed box, but you're out here in space. You can tell you're out in space because there's lots of cool stars. And I know what you're thinking, I should really give up astrophysics and go into some kind of art career. And I've considered it, I have. Now, the thing that's really cool about gravity is there is no experiment that you can do to tell you which one of those two situations you're in. Whether you're in free fall or whether you're out in space with no local gravitational field, they feel identical. Remember, you can't see outside, so you can't see that the ground is looming up towards you and you're going to die soon. So those two situations are completely identical. So this means that there are situations on Earth where you can experience weightlessness. And if you've ever been on a roller coaster, you probably have experienced it. So another cool PowerPoint animation coming up. If you throw a ball, you know kind of what happens. It moves in a parabola. You start off with the force that you've given the ball as you throw it upwards. Gradually, gravity overcomes that force and starts pulling it down so that it slows down to 0, and then it picks up speed as it comes back down, like so. So there's that brief period over the top, just like when you go over the top of a roller coaster, where you have this feeling of weightlessness. And so you can use this to achieve real weightlessness on, or at least near, Earth, by making a plane do that same parabolic motion. And this is a real thing. It's called the Boeing KC-135, also affectionately known as the Vomit Comet. And here it is, and it's going to go up in a parabola. It feels weightless for a little bit, and it dives back down, and so on and so on. And now that period of weightlessness lasts around 20 seconds, but it's enough that NASA has used it for some astronaut training. It's also used in movies. So there were a lot of zero-G scenes in this movie, and that's how they did it. They went up in the Vomit Comet. I do wonder, actually, if the vomit scene in the movie was real, possible. And this means, though, that they only get 20 seconds at a time to film all these zero-G scenes, so they have to do that parabola over and over and over again. It doesn't bear thinking about, really, rather than me. But this means that the zero-G scenes are really, really good. This one is my favorite. This is juice being squirted out, and it's a really, really quick scene, so I'm sure no one but me noticed it. But if I play that again, pay attention to what happens when the juice hits his hand. Ooh, sticks to it, see? And this is because liquid has surface tension, and so it will tend to stick to your hand rather than floating off all over the place. So those of you who are at my gravity screening may remember that I criticised the way Sandra Bullock's tears acted in Zero Gravity. This is how it should have happened, and the reason this movie that's almost 20 years older than Gravity did it better is they really did film it in zero-G. Now, I did discuss during the Gravity screening why they chose not to do this, and it is this problem of you only get 20 seconds at a time to film, which is fine for most of the short shots that you see in this movie. Gravity has a lot of really, really long shots where this wouldn't work. And you do get some mistakes pop up, like this one here. Pay attention to what's happening to this guy and to the roll of duct tape. Right there. You see they both move to the right at the same time. There it is in slow motion. They both move to the right. There. So this is the plane is making some kind of movement. That wouldn't really happen in space. So you do get mistakes crop up if you try to use this Vomit Comet that only gives you 20 seconds at a time to film, but I'm being super nitpicky. It was mostly really good. However, I do have another problem with this scene, so I'm going to play it again with sound.
One more thing, Jim. While Jack's working on the power-up, we'd like you and Fredo to transfer some ballast over the command module.
Say again, Houston, ballast?
That's a firm,
Well, you got to get the weight right. We were expecting you to be toting a couple 100 pounds of moon rocks.
Right, Houston.
The thing about gravity is if you're falling in a gravitational field in a vacuum, there's no air resistance, doesn't matter how much you weigh. So it's really unclear why the weight was a problem here. And actually, this is a true story, the weight was not the problem. The problem was that they were towing the Lunar Module, which of course should have been ditched on the moon, and the Lunar Module was venting some kind of water vapor or something out into space, and this kept pushing them off their trajectory. This is why they were saying that they were finding it really difficult to fly. It has nothing to do with weight, and that's a really, really basic law of physics that I'm kind of surprised crept in there. Overall though, as I said, I really think this movie does a really great job, and I have only really skimmed the surface, but I've been super nitpicky to find holes in this movie. And overall, it is actually pretty amazing. All of the interiors of the spacecraft, of mission control, these are all replicas. I read that NASA actually offered them the real mission control to film in, and they said, no, we'll make our own. But one of the NASA consultants working on the movie said that it was so realistic that he walked off the set expecting it to be on the second floor where the real mission control is, and looked for the elevator, and the set's on the ground floor. So it is actually really cool, and I really, really like this shot that we see at the end. At the top here is the scene from the movie. This is the damaged service module. They actually get their first look at the explosion as they jettison it. And on the bottom right here is the real photograph of the real damaged service module. And it's a pretty good replica, really. They built replicas, in fact, of the entire spacecraft, obviously with removable panels and things so they can get cameras in at different angles. Had to build versions that could fit inside this Boeing spacecraft. It is actually pretty amazing, and the attention to detail is incredible. And it really goes to show you don't need to break the laws of physics too much to make a good dramatic movie. So thank you very much for coming out. That is unfortunately all I have time to cover, even though there was so much science in this movie. So if you do have any of your own favourite bits that you want to critique, do feel free to join us in the bar afterwards. And we can go over our own favourite bits and other little mistakes. There's lots of like stupid little continuity errors and things in this movie as well. But overall, really, really great movie. Now, next month, 1 month today in fact, it's the 27th, isn't it? I do like to oscillate between the serious and the not so serious science movies, and this is one of my favourites. And our big challenge here is going to be, can I get up and give a talk after this movie without being a sobbing wreck? Possibly not. We'll find out. It'll be exciting. So this is July 27th, 1 month today, right back here at the Alamo Drafthouse Mueller. I hope to see you again then. Until then, thank you so much for coming out again. Thank you to Lara, who's filming tonight, and to my mom, who came all the way from France to see this. So have a great night.